We have our last conference. This conference will be done by Diane Larlus. Diane is principal research scientist in NAVER LABS Europe, and she works on computer vision. She will explain us the different aspects of computer vision and a specific point about the mass of data that are necessary and some example to reduce this need. We are very happy to welcome Diane for the second time. Her first conference last year has been very appreciated by students, so I think that it will be the same thing for you today. And so Diane, you can speak. I give you the talk, and thanks a lot.
Thank you very much, Pascal, for the introduction, and thank you for the invitation. And good afternoon, everyone. So I'm really pleased to be here and to share some of the research I've done the past few years, and some of the research problems that I think are important in computer vision, and most likely beyond. So today I'm going to give an overview of the research problem of lifelong visual representation learning. And during this presentation, I'll try to explain why I think this problem is worth studying. And I'll cover several of the recent research contributions that we've done in our team on this particular topic. But let's start high level, and let's start with one of my favorite computer vision tasks, that is the task of cat classification. So let's assume that you would like to build an algorithm that is capable of predicting when presented with an image if it contains a cat or not. So you want to be able to do that for any image you've never seen, right? So to build such an algorithm, first you need images of what cats can look like, which is surprisingly diverse. Optionally, you can use images of what cat shouldn't look like. And once you're equipped with this, you can train your favorite model, for example, a deep neural network, in order to be able to predict when a new image comes along that, of course, you've never seen during training. Then you can predict, your model can predict if the image contains a cat or not. And this is one of the many tasks that computer vision is about. So trying to define computer vision, it's when you're trying to automate something that is a high-level prediction task. So in other words, you're extracting semantics out of low-level information, such as sets of pixels. And computer vision has witnessed tremendous progress over the last 2 decades, especially for the task of image classification. And we'll look a bit into this right now. So what I would like to do now is really to review some of the key milestones over these last 20 years. So one of the reasons of this progress was that large image collections were made available to train these models. So when you look back in 2005, well, a joint effort from the Pascal European project focused on challenging images, opposed to the constrained images that were used in the past. And these challenging images contain one among 4 categories: bicycle, car, motorbikes, and person. And building such a large data set, large at the time, a few thousand images, this Pascal European project and some of the researchers participating in this project organized a challenge where participants were asked to classify an image among these 4 categories. And in 2006, they extended their data set to 10 categories. In 2007, it doubled again, reaching 20 categories. So the challenge continued being organized every year for a few years. And this was really key in computer vision because this allowed people to compare their methods for image classification on common benchmarks. And then they could compare different flavors of computer vision approaches and compare them on the same images for the same task. So really this boosted progress. But something happened in 2010. The ImageNet dataset was released. And for the first time, a full data set of 1 million images was shared for training computer vision models. And not only 1 million images, but each of these images was annotated with a label among 1,000 possible categories. So now participants could train on 1 million images to classify 1,000 possible categories and were evaluated again on a common test set, so the different methods could be compared. So there was a companion challenge, and it really became the new test bed for image classification. So we've seen that the first reason for the great progress of image classification was the fact that large collections of images became available. The second reason of this great progress was the rise of deep learning architectures that were using deeper and deeper networks. So those could only be trained thanks to the large data sets that I just mentioned, such as ImageNet. Before, it was not possible to train them. So now I would like to give you a bit more insight on what these deep models look like, what are they composed of, and I want to do that by giving you a history of the winning approaches of the ImageNet challenge. So the 2 first years of the competition, 2010 and 2011, the best approaches were still based on local handcrafted descriptors that were then aggregated into global representations such as the Fisher vector. So those would capture low-level information such as contours, textures, and they were really handcrafted. So there was no learning in descriptor part. The learning was only something you did on top of those descriptors. So that's why we call them shallow methods, because they don't really have multiple layers. They just have a classifier at the end. And these shallow methods, they were still the winning methods for image challenge 2 years in a row. And this type of approach, it's very efficient and it runs on simple CPU. But then in 2012, something happened. For the first time, an object categorization challenge was won by a deep architecture. And this deep architecture was actually a convolutional neural network. So convolutions are operations you can apply specifically to images. And this architecture was proposed by Alex Krzyzewski and co-authors. So this is why it's typically called AlexNet, because the first author of the paper is called Alex Krzyzewski, and it's composed of 8 layers, which was considered very deep at that time. And this was only made possible thanks to a very clever implementation of Alex Krzyzewski, where instead of running this method on CPU, they were actually running on 2 GPUs working hand in hand, and the implementation was directly in the language of the GPU, these graphical cars that were typically used for gaming. So really, like, big step, 8 layers was considered a lot, many parameters for these models. In 2013, another architecture was proposed by Zeiler and Fergus, which won the challenge with 8 layers as well. In 2014, the VGG network and its 19 layers won the challenge. So this one required to train a considerably larger number of parameters than the winning methods from the 2 previous years. So that's like we're really growing in sizes for the networks. Slightly deeper, 22 layers, but more efficient in terms of parameters, the GoogleNet architecture was proposed the same year. And as you can guess from the name, it was proposed by Google. And in 2015, the challenge winners were using the impressive ResNet architecture. So this one has 152 layers. So what the authors of the architecture had done, they have found a way to successfully train a convolutional neural network that deep. And this was possible thanks to a very nice contribution that allowed to train such architecture. But obviously, the fact that we have increasingly large networks that are trained on increasing large training sets, this has a consequence on the computational requirement of such models, right? So every time you need to train such a model from scratch, for example, to tackle this classification problem with 1,000 categories, well, this is very computationally demanding. So this is really something that, as the models grew larger, we had to start taking into account, and that's what I'm going to talk about next. So let's move on. If we summarize the reasons of this progress in computer vision for the past let's say 20 years, I would say that provided that you have a large collection of images to train from, a model with many parameters, and you can throw lots of compute at it, you can build classification models that can successfully classify hundreds or even thousands of categories. So now, if you'd like to classify the 1,000 categories of the ImageNet dataset that I showed you before, they're extremely strong pre-trained models that are readily available to do so. So now that's great. But what happens when a new problem comes along? So let's assume that you would like now to classify hundreds of famous landmarks. What you need to do is to collect a new data set suited for the task, retrain a model, throwing again lots of compute power at it. And yet another problem comes along. For example, you want to classify leaves, then you have to start this entire process over again. So dealing with each new problem from scratch sounds like a giant waste of time, of memory, but also of resources. So can we do better than that? And this is what we'll look at with lifelong learning. So in lifelong learning, you know beforehand that you won't be solving a single task in isolation, but many. And learning for one task should help learning for the other. And in some cases, the learning sequences can be very long and very complex. But for now, we're going to restrict ourselves to only two tasks, task A and task B, and we're going to look at two research questions. First, how can we train on task A so it's going to generalize later very well on task B? And the second question is, once you've trained on task A, you have a model that is available out there, how should you adapt it so it's going to perform better on task B later? And for the first part of this presentation, I'd like to go even one step further. So let's consider task A, and let's use it as a pretext task, not that we want to solve, but a pretext task to build representations, which by design will transfer to a task that is still unknown. So this is what I'm going to call training transferable visual representations. And that's what I would like to discuss now. So as discussed earlier, training from scratch is computationally demanding. Yet people have very quickly found out that models that are pre-trained on ImageNet are extremely useful starting points if you start tackling other computer vision tasks with fewer training examples, including other image classification tasks or object detection, instance segmentation, image retrieval, and many others actually. So now fully supervised classification on ImageNet, which was considered for the challenge I described before, well, this task, it could be considered as a pretext, as a proxy task to train strong visual representations. And that's extremely convenient, actually. But assuming that a fully annotated ImageNet size, so 1 million images training set, is available for your domain of interest, this is really a strong assumption. And this is probably not true for medical images. So what we would like to do is to reduce the annotation cost associated to training such models, and in order to build transferable representations. So can we reduce this annotation cost? And I'm going to mention two ways to do this, one based on self-supervised learning, a term that we'll define in a second, and one based on weakly supervised learning. So let's start with self-supervised learning. Remember, here our goal is to train transferable visual representations. And the standard way to do this that everybody follows is to use fully supervised classification, a large data set, for example, ImageNet. This requires each image to be annotated with one label among 1,000. And such fine-grained annotations, they require expert knowledge because not everyone can get the exact category of a mushroom or a bird right. So is there a way to train visual representations with images only? So no annotation is required. And this is what we're going to do, leveraging self-supervised learning. So self-supervised learning, it's a type of learning approach that is unsupervised. But the trick is that they borrow from the supervised techniques, except that in their case, The labels, they do not come from human annotators, like for the animals that you've seen on the left. But the labels, they are fabricated from the data itself. And I'm going to give you a few examples. So one of the early approaches for self-supervised learning is based on the proxy task of context prediction. So given a patch extracting from an image, such as, for example, this cat face patch that you see, and a second patch that is extracted in its surrounding, then the model is asked to predict the relative position of the second patch with respect to the first one. So as you can see, this is a supervised classification task. You need to choose one position among all the possible positions around the anchor patch. But the ground truth, the correct location, is not something that has been provided by human annotators. It is something that has been automatically extracted from the data itself. And by training a classifier to get this task right, over thousands of patches on thousands of images, you can build a model that is actually leading to very strong visual representations. And that was quite an interesting observation. I'd like to mention a second example because I find it quite intriguing because of its simplicity. It's a RotNet model, which is simply training by learning the correct orientation for an image among the 4 possible options. So here you have this image with sheep, and you want to predict which of the orientation is correct. Again, you do that on very large collections of images, for example, ImageNet, but without its label. And by training a model to do this, you get a model that produces pretty good starting point for good visual representations. So those approaches that I mentioned are some of the earliest ones, but many other pretext tasks have been proposed to tackle self-supervised learning. And among them, those based on contrastive learning have been quite popular in computer vision. So most of them have the same way of working. So most of them, they take an image, then they build 2 different transformations of that image. And then they learn an embedding function. So in other words, they learn the parameters of a deep learning model that will produce visual representations that encourages these representations of these 2 transform versions of the same image to be close to each other in the representation space and further apart from the embedding of a negative image. Ideally, any negative image. So in this case, the proxy task, the pretext task to learn representation is instance discrimination. Note that here, the negative that I chose for this illustration is a dog, but it could very well be a cat. It has to be just a different cat because we have no notion of labels, right? We just have images and we don't know what they contain. The labels are really something that is provided automatically. In our case, the only information we have are these 2 images, 2 transformations of the same starting image. That's it. If they're not the same transform version of the first image, then they're different entities. And we need to differentiate with those. So a key observation that can be made for these approaches is that making the proxy task more difficult leads to visual representations which generalize better. So how can we make the task harder? One thing you can do is to create better positive pairs. So these more challenging positive pairs, you can obtain them by crafting the set of the augmentations. For example, different transformations have been proposed, such as extreme color changes, some geometrical transformation, like heavy cropping, rotations. You can hide part of the image, you can apply filters. So this is a way to create more challenging positive pairs. So by creating very challenging transformations. Another way to make the task harder is to create better negative pairs. So by better, we mean more challenging, of course. But in practice, how do people do that? In general, to have more difficult negative, you can go for more negatives. So you increase the batch size. The batch is the number of samples you use at one time for training your algorithm, or you can use a memory bank. So you have more negatives that you keep track of and that you can reuse for your training. But what we observed is that after training a few epochs, so after a few training steps, the vast majority of negatives become easy. So they do not contribute to the training anymore. They do not help improve the model anymore. So how can we still have hard negatives to help for the training? What we propose to do is to rely on the few hard negatives that still exist. And we propose to mix the hardest negatives for each query and synthesize on the fly directly in the feature space additional hard negatives. You can do that by mixing two negative samples, or you can even obtain this by directly mixing the query with a negative. So we've called this technique mixing of contrastive hard negatives, or MOCHI in short. And this leads to models that train better and more importantly, faster than those who would not use these synthetic examples. Now I'd like to move to another way to reduce the annotation cost, and I'm going to describe a weakly supervised learning approach. So as we said, when category labels are available, you can build very powerful models, but these require fine-grained annotations that also require expert knowledge. At the end of the spectrum, you have self-supervised learning methods that I just covered. They work great, but they either use large data sets, such as ImageNet, or even bigger and less curated ones. So as a consequence, these approaches, they can be really computationally demanding. So in this work that I'm going to describe now, we were looking for alternative approaches, which would use captions as a source of supervision, but which would require fewer images. So now we're looking at a way to train visual representations from scratch using a medium-sized set of captioned images. And producing such captions, this does not require any expert knowledge. And sometimes caption can be collected automatically. So this is really something that I'm going to call weak annotations. So in this work, we drew inspiration from the recent advances in natural language processing. Natural language processing is a field where you predict, you work on prediction tasks on top of text, and those can be automated by a computer. So what did they do? Well, one of the things that was proposed in natural language processing is the masked language modeling task, where a token is randomly masked in a sentence, and the goal is to predict this masked token relying on the rest of the sentence. And solving this task leads to strong language models. So in our case, we don't have just text. We start from an image caption pair, right? Because this is what we have for training, images with their captions. So given an image caption pair, first, we mask a token in the caption, similarly to what I just described on the text. Then we try to retrieve the masked token using the remainder of the caption, but also the image. So in this example, we would like the model to leverage a visual representation to predict the word umbrella. Once we have defined the proxy task that we want to solve, we need a multi-model architecture to tackle it. So our model requires a visual representation. And remember, this is what we're really interested in. We want to train a good visual representation. The rest, this is just a pretext to obtain this good visual representation. We need a textual representation. So in our case, we assume it's provided, for example, following the approach that was described in just the previous slide. And we also need a model with a bunch of auxiliary modules to solve the task. And simply by training a model and representation to solve this pretext task, the visual representation that we obtain is actually very good to represent images and has been trained only on a small set, let's say 10 times smaller than self-supervised learning approaches, but with captions. So we call this task image condition masked language modeling. And I want to show you what is captured by the different visual representation here. So those are visual attention maps that are produced by our model for a given image caption pair as we mask different tokens in the image. So you can see that the model can attend to different image regions depending on the masked token. So let me go back now to the initial task we want to solve. Because we've seen that we can train visual representations by training a model to classify the 1,000 categories of ImageNet. We've seen that we can also use the ImageNet images without labels by building pretext tasks. We've seen that we can also use text that is proposed together with images to train good visual representations. But no matter how we build this model that creates a visual representation, what we would like now to do is to find the best way to evaluate that the representations we've built are in fact useful for something. So the problem here is that we don't know in advance which task the visual representation is going to be applied to, right? Maybe it's going to be image classification, maybe it's going to be detection. We don't know yet, maybe it's going to be something very different. But we want to build a visual representation that is going to be as useful as possible for future tasks as well. So we would like to evaluate the generalization capabilities of these visual representations. How can we do that? Well, the way visual representations are typically evaluated, it is simply by using these representations on a large set of tasks and data sets that is actually as large and as diverse as possible. And we just see how they perform on this task. And this gives already a very good first intuition on the generalization capability of visual representations. But can we think of something that is more principled? So let's focus on a single aspect of generalization. Let's focus on generalization to new concepts. So we look at the question, when training a model on a set of seen concepts, so maybe we've seen all the animals in ImageNet, for example, how well does it generalize to new unseen sets of concepts? So taking an example that is a bit more extreme, does learning about cats help us learn faster about caticorns, a category for which we have very few training images and rarely photographs, I would argue. So we would like to evaluate this generalization capability from a known class to an unseen class with a dedicated benchmark. So the benchmark I'm going to present is really dedicated to this evaluation of concept generalization. To build such a benchmark, first we need a way to define what is the semantic similarity between concepts, right? The intuition behind is that a tiger cat and a European cat are more related than a tiger cat and a cabbage worm. So this allows to rank categories from the most similar to the least similar semantically to a starting category. And the benchmark we propose is based on the same idea, except that we extend this measure to compute the semantic distance between sets of concepts. So if we really want the benchmark to truly evaluate concept generalization and nothing else, then the concepts should be the only thing which varies. So to allow that, to make this possible, we start from the full ImageNet dataset, not the 1 million images that I described at the beginning that was used for the benchmark, but the full dataset that was collected at the time that contains actually 13 million images. Then we define a set of seen concepts. So these seen concepts, these seen categories, are the only ones that the model are exposed to when learning visual representations. For this, we use the 1,000 categories of the ImageNet challenge, because many methods use them anyway to learn visual representations. Then we've built 5 sets of 1,000 categories, which are increasingly distant from the 1 categories of ImageNet. So to recognize these categories, this requires for the visual representation to have more and more generalization capability. And this gives us a full benchmark composed of a well-defined training set with the only classes that the model are able to see when learning visual representations, and 5 test sets of increasing difficulty that we call generalization levels that are unseen categories, which allow really to evaluate what we want to evaluate. And without going into the details of the study we conducted, we compared a very large number of approaches that were dedicated for learning visual representations. And what we found very interesting is that, surprisingly, the most resilient methods, the one that generalize best to unseen concepts, are actually the self-supervised learning methods that I described first. They're even better than their supervised counterparts. So this brings us to the end of the first part, where we've seen two ways to define a proxy task for learning visual representations, which required fewer annotations than the standard pre-training on the large ImageNet dataset and its labels. We've also seen how to evaluate a visual representation to see how well this representation generalized to new concepts in a principled way. So now for the second part, I'd like to go back to our initial motivation of lifelong learning. So remember, for lifelong learning, we assumed that we had many tasks that we wanted to tackle, not all of them at the same time, some first, some later, a few of them concurrently maybe, who knows, but we knew that we would solve multiple tasks and we wanted to reuse as much as possible the compute when training for one task before we started tackling the others. So now, instead of considering a sequence of tasks, so classification and then detection and then something else, we're going to consider a sequence of domain. So we assume that the task stays the same. For example, we keep our task of cat classification, but it's the domain which varies. So let me give you a toy example. We can assume, for instance, that we train a cat classifier with natural images. And then we adapt it. So we give a few more training samples. So we adapt it to deal with paintings. And after a while, we're interested in pixel art. So we get new data to adapt this model again, and then to adapt it specifically to pixel art, because this is what we want to classify now. So typically, it's easy to perform domain adaptation in such a supervised setting, because you get new data with their corresponding labels. You can simply update the model to take into account this new data you got. So the model evolved, and that's exactly what you want to do. This is lifelong learning. But there's a downside when adapting the model, because when applying the final model, the one that has gone through the 3 training phases, the initial phase, that is training for natural images, and then the 2 adaptation steps, one for paintings and one for pixel arts, when you apply the model back to the domains that were previously encountered, it has almost forgotten what it was initially trained for. So this is a problem that is very well known in the machine learning community, and it is known as the catastrophic forgetting issue. So in the last part of this presentation, what I would like to do is to focus on mitigating catastrophic forgetting when you're doing continual domain adaptation, to show you that although this always arises, there are methods to mitigate this issue in real systems. And now I'm going to jump to a slightly more realistic example than the cat classification. Let's assume that we want to build a navigation system for a self-driving car. So the self-driving car needs a visual system, and this visual system has been trained for a particular environment with the data available. And we would like to be able to update this visual model as training data for new domains is provided. So maybe you get snow images, fog images, sunset images. And as this new weather condition or new environments come, then you get data and you're going to update your model accordingly. But without precaution, as we just mentioned, as the model gets updated, it is likely to forget the previously learned patterns. This is what I called catastrophic forgetting. And what we would like to do is really to mitigate this catastrophic forgetting. So a naive solution to counter this is simply to keep in memory all the encountered training examples, the initial ones, the ones from the different steps. We keep all training examples and we retrain the model from scratch with all data available every time we need to update a model. And that works extremely well, actually. But it is obviously intractable for practical reasons because of how much it would cost in terms of time, of memory and of compute. But on top of this, it's not always possible to store previous training data, in particular for privacy reasons. So sometimes you provided with a model, you don't have access to the data that has been used to train it. So you need to be able to update it without this information. So in our work, we wanted to focus on a method that doesn't store any samples for retraining. How far can you go? You can't store anything. How much can you mitigate catastrophic forgetting? Well, one thing you can do is to heavily randomize the visual appearance of the current domain samples. So here, randomizing the appearance means applying image transformations that can heavily alter the appearance of the image. So you can see that all these images are fairly different from the starting point, but these transformations alter only the appearance. They do not change the semantics, which means that if you have labels, the labels stay relevant for the task, right? And intuitively, if you do this, if you apply domain randomization, this increases the model's comfort zone when training. So this is the process of adapting to different domains. And in turn, this results in models that forget less. But you can also leverage these transformations in a more principled way. And now we're going to call meta-domains each set of samples that we obtain for a given transformation. Here we have our current domain, so a set of images to train from. And then if we choose 3 different transformations, we can create 3 meta-domains on this example. And our proposed solution, it relies both on domain randomization that I mentioned before and meta-learning. So it will train for the current task. This is what we really want to do, right? Train with the data we have. But we're also going to train, keeping in mind that we want to adapt faster to meta-domains. And we're going to train with an objective that makes sure that we mitigate forgetting on those meta-domains. So we're going to have these 3 components that are used in a single learning objective. And this is how we're going to train our model. And by doing that, we can train a model that is ready to be adapted and that is going to be more resilient to the forgetting. Because everything happens during training, this is really neat because this technique can be deployed without changing the existing pipeline. This is just changing the loss function, the objective you train. You don't change anything in the rest of your pipeline. So you can just apply it every time training set is provided in sequence of training. In other words, every time a domain is encountered. And we experimentally observed on a number of tasks involving classification, but also segmentation, and I will talk about segmentation in a minute, that indeed, by doing this, we can still mitigate the forgetting without storing any past samples for retraining. In the last piece of work that I want to describe, we're going to go even one step further towards an even more realistic scenario, where here samples, they do not come as batches, but they arrive sequentially as the environment continuously changes. So you can imagine you have your car driving and you get like sequences of training samples. And on top of that, those are unlabeled because you get new images, new frames, maybe new data with it, but absolutely no human labels. So now the goal we want to tackle is to adapt to sequences of samples that are temporally correlated and unlabeled. So you can see it as each sample that is acquired that triggers its own individual adaptation problem. So now, how should you perform adaptation in that case? So if you look at what's done, all the existing benchmarks assume access to a label validation set, an assumption which is not valid for many realistic scenarios, including ours, because we cannot get new data and have something labeling them as the data comes. This has to run on the fly. So for this work, we've more specifically considered the task of semantic segmentation. And semantic segmentation is another standard computer vision task, because until now we've looked at image classification. But semantic segmentation is another standard computer vision task where the computer is asked to assign each pixel of an image to a label, depending on the object containing that label. For example, in these annotations here that were produced by humans, so these really human annotations, all pixels belonging to the sky have been colored in blue. All pixels that belong to a tree are colored in green. Cars are in blue, pedestrians in red, and pavement in flashy pink. So now we would like the model to predict these labels and not like and on new images, right? These are human annotations, but we want to do that to new frames that are encountered. So on top of the standard semantic segmentation problem, here we will not just label the pixels of a single image, but we're going to assume that we want to label all the frames of a given video sequence. And we're going to assume that the different frames of the video arrive sequentially, and we have to deal with them sequentially. And if we go back to this example of the self-driving car, you can totally see why the environment would change in our context, right? The car would drive, the environment will change, the nature and the appearance of the objects would change. Maybe buildings are different, depending if you're in the really heart of a city or if you're going a bit further away. And you also have like gradually shifting domains, right? Because you're not going to have exactly the same amount of pixels for each categories. Some classes will appear, some classes will disappear. So we have to deal with this shift. So to tackle this task, we also use the benchmark that really model what is going to happen in a real world scenario. So it's composed of 3 steps. First, the segmentation model is trained in a regular way offline. This produces the initial model that will be used later. Then this model is used to initialize the model of the next step, which gets continuously adapted as new samples are required. Now we're going to compare multiple adaptation methods, and they depend on many hyperparameters and design choices. So to validate them, we use a dedicated validation step in order to choose the best flavor of each approach. And only the single best model according to validation is deployed on the test set. This way, models can cheat and can validate their parameters on samples from the test distribution. Instead, in this case, the test distribution remains unknown, which is really required for proper evaluation. And we use this benchmark to compare several approaches for adaptation. First, we consider, as in the previous part of the presentation, domain randomization, which again, if you remember, means that you heavily randomize, you heavily modify the appearance of the training samples. And this works extremely well because it reduces the chance of test samples to be perceived as out of distribution. So it's a very easy, but also very strong baseline to implement. Next, we've considered self-training using pseudo labels. Remember, the new frames that come, they're not labeled. So how do you still make them useful for training? Well, in practice, we can use the current model to perform a prediction. We trust some of predictions because we can look at the one with the strongest confidence. Then we use those as ground truths to update the model, and we repeat. So we do that as the frames come. And the last thing we consider is updating batch normalization. So batch normalization is a standard tool when training deep neural networks that help with stability. And it contains a few parameters that need to be properly learned. And it turns out that the adaptation of just the batch normalization statistics is known to improve model performance at test time. So here, every time a new sample is added, we adapt the rescaling parameters of the batch normalization. And we observe this strategy to generally help. Yet, the main problem with all the solutions is that, again, we witness catastrophic forgetting. Because we are learning to adapt in an unsupervised way. So it's really not trivial to know how one can prevent the model from drifting away and starting to completely lose the appearance of some classes, forgetting some classes. So in practical terms, we observe that rare classes tend to disappear and they left space for the more frequent ones. So what can we do about this catastrophic forgetting? There exist some countermeasures. So one thing you can do is naive learning. Instead of doing continual learning at each frame, Well, what you do is you do continue learning at each frame, restarting from the original model. So you don't adapt sequentially, you adapt starting from the first model every time. So you can't leverage the fact that you have multiple frames, but at least you're sure not to forget. Something else you can do is to use a memory bank. You can keep a few original training samples, and you can use them from time to time for retraining. So that's extremely powerful. But as we discussed a few minutes ago, sometimes you simply cannot store samples for privacy reasons. And finally, something that that is very easy to implement is a reset strategy. So this would be a strategy that looks at a number of properties of the model as it gets updated. And when some threshold is met on these properties, like kind of detecting that some classes disappear too often or something else goes wrong, then the original model that has been kept as a checkpoint is reset and reused as a starting point. So you can see it as a smarter version of the naive learning, which would use the naive learning approach only when the model detects that something goes very wrong with the adaptation. And although quite simple to implement, these reset strategies, they work extremely well in practice. I would like to show you a video that shows what's happening. So you have the input video on the top part here. Then you have, without updation, what's happening? Without updation, you see that the model is getting more and more errors, especially because we start having sunset. So the appearance of the different categories changes with this different lighting condition. When you continuously adapt, you start being more and more confident with the very frequent classes, but you tend to completely forget about the very rare ones. And with reset, this is a fairly acceptable trade-off where you still have a few errors because it's a very difficult task, but you do not forget entirely the rare classes. And you can also have a model that sequentially adapts and can deal with this very strong appearance change due to the illumination change, going from the daylight to sunset. So this brings me to the end of the technical part of the presentation, where I've shown a few research questions and some of the contributions we've made in the team to tackle these research questions. And as we're approaching the end of this talk, I'd like to bring all those pieces of work together to draft a take-home message. So we've seen quite a few research questions. We've seen different experimental protocols, different tasks, classification, segmentation, a few others. We've seen quite a few domains, but all these research questions were related to lifelong learning. And I would like to see with you, like what take-home message we could draft that would generalize beyond the natural images that I showed you today, for instance, to medical images. Maybe that could be of interest to you. And by doing that, I'd say that we've progressed on several research questions. So first, if you have to automatically deal with visual data, which visual representations could you or even should you use? Well, as a first option, be aware that many strong pre-trained models are readily available. Many of those models will produce visual representations that work as is. So you can use them directly as black boxes. Also, you could slightly improve them by fine-tuning these models with the little data you have. Fine-tuning is the term that we use when you like adapt a bit the model depending on the new data you receive. So in other words, rather than training a new model from scratch, which is going to require lots of data, lots of compute, you could and probably should, depending on your task. Well, there are cases where you can't, but you could look at pre-trained models. Second, how should we pre-train visual representations, right? Like, if you have no choice, you need to pre-train visual representations for a domain where you have absolute zero data or cannot use them for very good reasons sometimes. What can you do? Well, I would like to state again that self-supervised learning is a great tool because such methods do not require labels. So you can already beforehand pre-train something very strong without labels. And as we've seen later, once you have this model, you can slightly adapt it for the task that you need, but you have a great starting point. So which self-supervised learning method can you use? Many pretext tasks exist, but I would like to mention that invariance to data augmentation is one of the most standard ones. And let me state again that self-supervised learning have fantastic generalization capabilities. So they work great even on unseen categories and tasks, as we've seen in a few examples today. I'd like to state that text is a great source of supervision. We've seen an example where text has been used to reduce the amount of training data to be used to train visual representations. But other research has been conducted and showed that when you have lots of image and text available, you can build very, very strong models. So such large models that are sometimes called foundation models, like the CLIP model that you may have heard of, already significantly impacted the field. And I think that multimodality is going to be central to many state-of-the-art systems. So this is a field that I know less, I need to confess, but I've seen several very impactful papers that successfully combine medical images and textual information for improved prediction. So this is something that is also very used, multimodality, in the medical domain. As we've seen, it is a good idea to start from a strong visual representations, especially if you're planning to use it for multiple tasks simultaneously or sequentially. So the next question that we're going to consider now is, how should you pre-train visual representations so that they transfer better? And today we've seen multiple evidences that making the proxy task more difficult actually leads to better generalization. And we've seen how crucial data augmentation is to self-supervised learning, but also to continual learning. So really think about this when you're designing your pretext task. Finally, how can you mitigate catastrophic forgetting during transfer? Well, we've seen how in general, stronger pre-trained models tend to forget less. So intuitively, if the model is already very good and generalizes well, then it requires fewer training steps to adapt. So it is less likely to forget. One way to also forget less is to impose the training to favor solutions for which adaptations to a new task is likely to leave the initial task unaltered. Last but not least, you should put in place systems that detect catastrophic forgetting, and that's the only way such adaptive models could be deployed in the real world. We've explored a single research strategy, but there's probably a lot more that needs to be done in this direction. So this brings me to the end. Thank you very much for your attention. All the work that I've covered today has been done in collaboration with many great researchers that I would like to mention and thank in this slide. And now I would be happy to answer any question you may have about this or how this can be applied beyond natural images.
Thanks a lot, Diane, for this wonderful presentation. We start with the discussion. Have you some question? You can write it in the chat if you cannot speak. So maybe to start, I was very interested by the importance of the text, because in fact, if I have well understood, the text can help to the identification of image. And in medical imaging, we have a lot of image, but with this image, we have a lot of text, the report of the specialist. And do you think that we can imagine to use this report, this text report, to do some learning, and to do something like you have described about learning for image, and to help to develop algorithms to recognize the image, for example, on a scanner, radiology, or something like this.
So that's an excellent question, and I'm clearly not an expert, so I'm really going outside of my area of expertise. So I will try to answer my best. But from what I've seen, there are quite a few very nice papers that are doing exactly that. That compensate for the fact that sometimes you do not have large quantities of images like you would have for natural images, for example, to train better visual representations by leveraging the text that goes with it. So it has been done for creating purely visual representation for purely visual task. For example, detecting things in medical images, locating things, classifying for special types of symptoms, or, and sometimes it has been used for things that are a bit more complex, where text is just not a way to create pure visual representations, but it has also been used for predictions that would require understanding the entire set of modalities.
Okay, thank you. There was a question. I don't see. And if we look at in your take-home message, you describe a kind of workflow, in fact, a workflow, and some kind of strategy to apply to a project. And also in the medical domain, what strategy seems to you the best to apply if, for example, we want to train an algorithm to recognize some image of tomography scanner, something like this?
So again, I'm not an expert.
Yes, I know that.
So I don't want to say anything that is not accurate. But from what I know, many of these techniques can be applied. So I've seen in the past many prediction tasks involving medical images. So maybe CT scans or MRIs that would use models pre-trained on ImageNet first. This ImageNet is this very large data set I presented with 1 million images classifying like standard semantic categories. And this was used as a starting point and then fine-tune on medical data. Because if I'm not mistaken, sometimes you don't have access to large quantities of data. So you cannot really train from scratch an entire representation with just medical images. And there is some generalization between natural images to other types of domains. So this has been done and this has been successful. And I also mentioned the notion of privacy, right? I guess that sometimes you have access to limited data for good reasons. So it's a good idea to start with something that has seen some properties of visual data and then to adapt it for different modalities. I would like to mention that if we look at what these models have captured, even if they're trained to recognize cats and dogs, part of these models, they already learn to recognize very specific patterns that generalize beyond categories. So if we look at these deep neural networks, they capture contours, they capture texture changes, they capture color that is probably relevant in many medical images, but they capture a lot of other properties. So those are already encoded in the model that we use as a starting point if we apply that then later to a medical domain. And then this is why we can train a model with fewer training data and still get very reasonable results.
Yes, yes, it's very important for some kind of disease of pathology for which we have a small set of data, a small set of image, and I think it could be applied to this kind of disease, and it could help us a lot. Okay, we have a question from Eba Al-Kadi. is lifelong learning just for machines and artificial intelligence?
So lifelong learning is a term that is used in machine learning indeed. And it's a recent research direction, I would say, for learning models. So it's really something that applies to statistical models, right? For making predictions. And this is really something that emerged because before we were working on smaller sets of samples, and we generally started tackling problems from scratch, and that was kind of okay. But now we are going towards larger and larger models, more and more powerful models that are fueling what we call now AI. These very large models, they're extremely costly. So we need to think about ways to create them generic enough, reusable, transferable, so we can reduce the effort into building a new model for a new domain or a new task. So reusing, transferring, and this is very important for, as we said, because of the compute, but also because we don't have enough data for some tasks. So it's good to be able to share and transfer.
Okay, thank you. We have another question from Solano Todeschi. Can we consider deep reinforcement learning as a type of lifelong learning?
Good question. Yeah, reinforcement learning is really one way to train models with a very powerful way to define the objective function that is really applicable for let's say platforms that would have to, for example, interact with an environment. It's very used in robotics. That makes a lot of sense. And it is true that we have this notion of a model being updated, but there's still two complementary set of techniques that could be used together.
Okay, thank you. Another question from Victor Conte. Sorry, I didn't quite understand what a domain was. For example, considering medical image, like a tomography scan, what could be the domains?
So I didn't really, yeah, that's a very good question. Thanks. I didn't really specify a domain beyond this example. So I've talked about the domain of natural images, the domain of paintings, and the domains of pixel art. So basically, a domain would be the expected data distribution for your input. So the appearance of your pixels, the type of pixel, the type of colors, the type of texture you would observe would depend on the domains. So in computer vision, domains are, for example, these modalities here, like painting, natural images. We can call domain, for example, you have images taken during the daylight and images taken at night. Obviously, the appearance change between the two, the distribution change. So we're going to call that two different domains. And in the medical images, you will have like big domains, for example, MRIs or CT scans or, like X-rays. So these would be very different domains, but you can even have subdomains where everything I talked about is still applicable. Maybe you would have a certain machines that produce certain types of CT scans, right? Because of the resolution, because of something. And then a different machine would have slightly different data distribution. So maybe a model trained on one machine is not directly applicable to the other machine. So you need to adapt. So by domain, I mean the data distribution that is typically produced in this context. And this context can be a special camera, it can be a special machine, a special piece of equipment. I hope it's clear. I'm hoping, yes. I'm sorry that it was not clear during the presentation. Might have would have helped.
It's clear, Victor. Thank you. So does it mean that, for example, it should be interesting to have different for the same pathology, for example, a cancer, a tumor, to have the different aspects of this tumor using different methods of imaging, as you said, CT scan, X-ray, etc., etc., and that it could be so interesting to have this different aspect of the tumor with different machine. Let's say that, and finally, it is more interesting that to have several thousands of image using the same technology of this tumor. I am clear.
Yeah, very clear.
Okay.
It's a super relevant question, and I think this is also one of the direction towards which the field is going, because well, I can first talk about what I know very well, computer vision. We've been lots of progress when combining multiple modalities. So just not only images taken with a standard camera, but maybe you have depth information. You know, like indoor, you would have what the Kinect produces. It gives you a depth map. Outdoor, you can have some kind of device put on top of a car, like to obtain the depth information. Maybe you can have information that is providing information beyond the visible spectrum. And we've seen that if you have access to these multiple inputs, these multiple modalities, it's a good idea to combine all this because you get more reliable predictions. And I'm absolutely certain that there must be papers in the medical domain exactly showing that as well, because this is very relevant. And as we have access to now like very different machines, and they're showing different aspects of the same symptom of the same body part, maybe it's a good idea to combine this different information, and machine learning models capable of fusing multiple modalities in order to produce a single unified prediction, ensembling all these inputs. Machine learning models are ready. They're really good at doing that. So it's obvious that this should help also in practice.
Okay. Thank you. That's very interesting. Okay, have we got some other question? Scott asked me, do you mean the combination of, for example, cancer histology and CT scan? I mean, in the basis, CT scan, X-ray, or other technique of imaging, but you're right, maybe we can also merge some image from histology in this different kind of multimodal evaluation of the tumor, for example. Do you think that we can merge some image from histology? You know, histology, we have a microscopic image, but it's an image, in fact. And do you think it's possible to merge with CT scan, for example, that is a pixel image, or something different?
So I'm not sure I know what histology is, but from what I understand, these are two different images that are capturing something completely different, but for the same patient, right?
Yes, it is a different representation of the tumor, but in image of histology, you have the tumor and the aspect of the cell with different colors. And of course, it is globally the same thing that the tumor when you have a CT, for example, something tomography. Maybe it could be a good idea. I don't know. It's a very good remark, Scott. I don't know.
But that's as long as the modules are adjusted for this, right? You would not use the same deep learning based representation in the going back to what I know, right? Going back to the example I have here, and maybe other representations are standard. And I apologize if I'm, like saying something that doesn't make sense. But if we were to reuse building blocks, what we've seen today, to represent these two very different inputs, of course, we wouldn't have the same model to represent both, right? We would have a model specialized for histology, a model specialized for CT scans, and a module that would kind of ensemble the descriptors obtained from both, the prediction obtained from both for a final prediction. And I would like to go even one step further, like going back to text as a source of supervision. Maybe we can have like description reports because I'm sure there's always an analysis in plain words of some of these results. And if we wanted to build some kind of prediction system to help the physician produce even better results, why not also using like textual description, medical records, if that's something that is possible in terms of, you know, data available and privacy, which is a completely different debate that that needs to happen as well, of course.
Okay. Well, that is very interesting to think about and to imagine new methods. So in fact, we can merge some different techniques as a self-supervising learning with text, and also maybe pre-trained visual. Okay. So thank you. It was very interesting, and I think that the responses are very interesting for our students that are more specialized in image. Have you got other question?
Yeah, I had one more question.
Yes, Scott.
Yeah. So I just sent in the chat the question about histology, and now you said that you could combine, for example, a description of the image. So I will send another image, which is about endometriosis, for example. So let's say you have this image and you have the description from the pathologist who says the image contains endometrial stroma and endometrial glands, but he wouldn't, so the pathologist wouldn't actually annotate what is what, but just you have a text which describes the image and you have the image itself. Could you also somehow merge this information and that the network finally learns to recognize what is meant by stroma, what is meant by glands, or by whatever description?
So I'm looking at the images.
Yeah.
They are fairly different from the one I'm used to.
Yes.
And I know that you have specific techniques for these types of predictions, because there are a few things that are so already is the idea to classify or to localize, probably to localize, right? You want to segment what's happening there, right?
Yes.
Then you need segmentation techniques. The segmentation techniques that I know are more, well, they're typically developed with natural objects in mind. So you would probably have to develop segmentation algorithms specifically for those. And I know there's a very rich literature that I don't fully know. So yeah, I cannot really tell you how to approach this. You would have to ask an expert in medical images. You have entire conferences with papers everywhere on specifically tackling prediction tasks on medical data, with fascinating papers. Great progress, but this is really not a field where I'm an expert.
Yeah,
all right.
It's difficult.
Thank you anyways. Thank you very much.
Thank you. But maybe, Scott, one way to merge different kind of image should be to add the histology with the GEMSA and histology with another dyeing, histology with immunomarkage. So you have different, the same image with the same tissue, but you have different aspects of this image because you use different dye, different antibody to make immunomarkage. And I don't know, but it's quite the same thing to have an X-ray image of a tumor, a CT scan, a scintigraphy, different technology. Maybe it could be interesting. I don't know.
Yeah, that's right.
Maybe
that's
you
right.
have to dig this possibility.
Yeah.
Okay. So I think that we no, I don't see other question. What's more, Diane, thanks a lot. It was very interesting to see all this method and to see the improvement year by year. I think that if we invite you next year, we will have another technique. And I hope that all students appreciate this presentation. And I think we can stop now the conference. And thanks a lot once more to you, Diane. Okay.
Thanks a lot again for the invitation. It was my pleasure to be here.
It was our pleasure.